Hi Rocketeers, I'm Charlie Garcia, and in this special episode, we're going to be talking about liquid rocket engines. But instead of talking about my rocket engine, we're going to be talking about a very big, very excellent rocket engine built by the wonderful engineers over at Blue Origin. The BE-4 engine produces about 500,000 pounds of thrust and is intended to be used on several new rockets, including the New Glenn vehicle and the Vulcan rocket being constructed by the United Launch Alliance. This rocket engine runs on liquid methane and liquid oxygen. It has a closed cycle engine. That means that it uses the exhaust from its preburner is redirected into the combustion chamber to maintain extraordinarily high efficiency. And it's a wonderful looking engine that's intended to be reused many times. And recently, the United Launch Alliance released some excellent imagery of it on their Twitter page. And I just wanted to take a deep dive into that Twitter imagery today and see what we can glean about this awesome new engine. So this first image we're looking at here was released by the United Launch Alliance on July 1st, 2020 on their Twitter page. And it appears to show one of the first BE-4 engines arriving at the United Launch Alliance factory. This engine, Tori Bruno has stated, is a instrumented engine for development and not a final configuration engine. And I think that's pretty evident by the sheer amount of harnessing visible on the engine. So we're going to take a look and deep dive into what all these parts we can see do and mean. On this first part we're going to take a look at is this structural component between this yellow W-shaped beam and what appears to be the aux head of the engine, that light gray metallic structure and that bright yellow W-shaped widget. There is what appears to be an allodyne, that is a corrosion-protected piece of aluminum, attaching the two together. This appears to be a piece of flight hardware. So I think that probably what will happen is it'll be unbolted from the yellow connection, and that will be attached to a gimbal structure on the thrust assembly of the rocket engine, in this case the Vulcan vehicle. This is important because it kind of is going to ground, this is our reference point for the entire engine. So this is located directly on the center line of the engine at the very top of the engine. It is the significant structural connection between the ground support equipment, that is that blue and yellow cart that's driving the engine around, and the engine proper. We're going to start by taking a look at the cart real quick. So the first thing we see here is this yellow assembly. This is a breakover fixture. So if you want to work on the engine vertically, it appears that it would be bolted to some other piece of equipment through that puck on top of the engine, and that when they want to transport it, they then bolt it onto this yellow fixture while it's in the upright configuration. And then this yellow fixture actually rotates 90 degrees to the horizontal position, bringing the engine over with it safely. If you look kind of down and to the right of that yellow fixture, you can actually see the very large, I would guess that's maybe a 2-inch steel pin going through some bearing pillows that enables that whole fixture to rotate. And you can actually see there's some blue beams on the inside of the long blue rails that actually rotate with that yellow piece. That whole fixture is what allows the engine to be tipped horizontally in a convenient fashion. If you look further to the right down the engine, there's a aluminum fixture on a red kind of hinge point that supports the back end of the engine, and that's the other degree of freedom supporting the engine from kind of bending downwards when you do that. So essentially you'd lift the engine on a crane, bolt it down to that yellow piece, tighten up that aluminum band, and then you'd be able to tip it 90 degrees. And this is, in ground support equipment like this is really what makes it possible to build rocket engines effectively, economically, and quickly. And there's a lot of tight access points and hard to get at pieces of a rocket engine, not to mention the fact that they can be extraordinarily heavy, especially when they get this large. So having equipment like this that makes it easy and quick to attach cranes is really a lifesaver. So now we can talk about the various pieces of the engine. Just real quick, this bit circled in yellow up near the top of the engine, this is the Powerpack. This contains all the turbo pumps, the turbines, the pre-burners, and the instrumentation necessary to make that run. So this is what generates the high-pressure fuel necessary to operate the BE-4 engine. This assembly off to the right here is the nozzle. I believe it starts as a piece of copper based on some imagery I've seen. It appears to have been coated in something. If I were to guess, I would say they machine out a piece of copper and then either weld over or nickel plate over this closeout for the cooling channels. But this assembly is part of the thrust chamber, and this is really kind of the only part of the thrust chamber we can see is this nozzle extension sticking out to the right. The rest is buried under all of the harnessing and instrumentation and tubing and the power pack itself. So something I would expect to see on this main oxidizer valve and this main oxidizer inlet would be a bellows. And bellows are these flexible metal assemblies that you can see on the screen right now, and these allow the engine to deflect a little as the thrust vector control system hydraulics tip the rocket engine from side to side. This allows the fuel flow connection to stay intact and providing, tank pressure fuel to the turbopump inlets. And so here on the screen, I've pulled up some reference images for the SSME bellows as well as the J2X bellows, and you can see that they consist of this corrugated metal structure, and then they also have the support structure that keeps them from just ballooning out under the pressure into like a full-sized accordion. That helps react those forces. So despite not seeing those bellows, we can look and we can see there is a fuel tube kind of in this U shape that leads from the oxidizer inlet to the oxidizer turbo pump. And it kind of bends in this shape. We'll talk more about why it does this in a second, but this is going from the oxidizer inlet to the oxidizer turbo pump on the Powerpack Assembly. And here we see that corresponding other side of the engine. This is another view of the engine I believe someone took on Twitter. I will figure out where I found this image and put a link down in the description, because this individual got some excellent imagery. But this is that fuel inlet. So you can see there's no valve on this side, at least not that I believe to be a valve. So you can see the power pack a lot better here, that stack up of kind of staggered circles and half circles that make up that whole assembly. So I want to talk for a brief second about why all those tubes are bent and curved in these weird fashions, everything from the small tubes to the big tubes. So here we see a blank structure diagram, and these thick lines with these thin kind of diagonal lines is just a structural engineer's way of saying that there is fixed surface. That is, that anything that attaches to this won't be able to move or bend. It's just kind of stuck like that. And we can imagine some pipes. And let's start by imagining a pipe that is cool and just at room temperature carrying, room temperature fuel. Or maybe it's even cryogenic fuel. And it has some length. Now let's imagine that because the rocket engine makes several thousand degree Kelvin fire, that tube gets a little hot. All materials have this property called coefficient of thermal expansion, which describes how when a material heats up, it gets a little longer, a little wider, a little thicker. The atoms have to physically spread out a little bit because they're vibrating more because of their additional thermal energy. And this coefficient of thermal expansion means that the tube that was originally some length has gotten a little longer. Of course, this is a problem because we have defined that the walls of this contraption cannot move. In reality, you can imagine that this just means that the tube is attaching to some much stronger part than itself. So that means that the tube can't just get longer. What it has to do with that extra length is it has to bend. So it bends in the middle and it bows out. But let's imagine that maybe running next to that tube in this densely packed nightmare that is an engine, there's stuff everywhere, it's complex and dense, and there's lots of features. Perhaps there's a wire right next to it. And perhaps this wire touches this now several hundred degree hot Inconel or stainless steel tube. We can imagine that that wire might catch fire and burn through. And if that wire happened to control something important, such as a valve or a piece of instrumentation necessary to protect the health of the engine, we could imagine that a very bad phenomenon could result. And this is just one case of why these tubes bending in unpredictable ways is bad. You also can imagine that that tube is putting some stress into the walls where it's pushing on them, and this is undesirable. So what we want to do is we want to find an elegant way to mitigate the stresses induced by the thermal differences in our tubing. And so what we see on this engine and on a lot of other rockets is that we can add these features to the tubes that allow them to deform in known fashions. So kind of on the left, we have a cold tube that evolves into a hot tube. And when it does that, what we see is that with this kind of two bends in it, the tube on the left can get longer, the tube on the right can get longer, and conveniently, that tube in the middle will get longer as well. And this will allow the tube to stretch in the middle without adding particularly undue stresses on the points of origin of the tube. On the right, we can see another example of a way to do this. It's a cold tube with a loop in it, and when the tube heats up, the loop grows in diameter, but the tube maintains the same overall length, and there's, once again, limited stresses on the ends of the tube. And remember, all of these work in the opposite direction as well, so if you run a cryogenic fluid like liquid methane or liquid oxygen through what was originally a room temperature tube, it will shrink and try and pull those two walls together. and you'll have the same problem again in reverse. So that's why when you're looking at this engine, you see all of these tubes being kinked and bent at all kinds of weird angles. Not only is it to enable the tube to fit around and over and between things, but it's also to provide opportunities for the tube to bend in elegant ways that doesn't put a lot of stress on connection points. So what we see here is the Powerpack Assembly. The Powerpack Assembly provides the energy necessary to turn low-pressure tank fuel into the high-pressure fuel you need to inject into the rocket engine. So let's take this opportunity to discuss how we get that energy we provide to the fuel to raise its pressure. The BE-4 uses what's called an oxidizer-rich single-shaft closed cycle. That means that you burn all of the oxygen with a little bit of the fuel in a pre-burner to generate lots of high-temperature gas. And you can take this gas and flow it over a turbine, just like you'd find in a jet engine or a power plant, to generate torque. And this torque spins 3 pumps that raise the pressure of the fuel and oxidizer, enabling it to be injected. But instead of wasting all that high-pressure gas you generated, you inject that gas back into the combustion chamber as well, enabling you to get a very efficient, very high-power, very dense cycle. So if we look back at the power pack, we can see how torque and fuel and oxidizer flow through this engine. So we're going to start actually at the far left of the image, and this is the bottom of the engine. So fuel flows up through this kind of swoopy connection here and around this right angle fitting. And at this right angle fitting, we actually have something called an inducer. An inducer is a special part of a turbopump that helps raise the pressure and prevents cavitation. Cavitation is a phenomenon where the turbopump raises the pressure by so much, there's so much suction at the front of the turbopump, that a little bit of the liquid actually turns into a gas. And these little bubbles of gas then can collapse catastrophically. And this creates pressure spikes, little pops, that can be very detrimental to the surface finish of the turbopump and can destroy it actually. So what you want is enough pressure in the fluid that these little bubbles can't form. And you do that by creating this kind of very oddly shaped bit on the front of the turbopump that kind of pre-squeezes the fuel so that it can efficiently reach the turbopump without this cavitation phenomenon. So the turbopump spins around very rapidly, several thousand times a minute, and that turbopump slings the fuel to the outside diameter, and you can kind of see this like gray half-circle feature stretching around the entire outside of that turbopump. That's called a volute, and the volute accumulates the fuel and slows it down, and because of the dynamic pressure relationship, whenever you have a fluid that is moving quickly and you slow it down, the pressure increases. So this is where you get the first pressure rise of the engine. And so you can see that some of that fuel goes off to the bottom left there into the regen jacket. That is, it flows through the inside of the nozzle, in between the outside of the nozzle and the inside of the nozzle to cool off that metal and keep it from melting under the incredible temperatures. And this fuel doesn't need to be very high pressure because it only needs to be high enough pressure to enter the combustion chamber. But a small, about 1/8 of the fuel, maybe even a little less, maybe 1/12 of the fuel, goes through the middle of the turbopump into what's called the booster pump, the boost pump. The liquid methane boost pump raises the pressure of a very small amount of the fuel even more. It raises it, possibly to 10, maybe 10,000 psi. I don't know the exact figures for the BE-4 engine, but possibly to very high pressures. And this is necessary because this fuel has to go get mixed with the oxidizer to go through the turbine. And the process of going through the turbine will reduce the pressure some. So this needs to be at a much higher pressure than the rest of the fuel in order to enable it to enter the combustion chamber. So that fuel kind of goes straight down and then it bends around the backside of the power pack to go up to the top. That is the far right of this image. So we'll look at that again in a second. So let's look at the next pump to the right. That's the Lox Turbo Pump. So in the previous images, we saw how the liquid oxygen kind of comes through that U-shaped pipe and up into this feature here. So this pump right here takes the oxidizer and it raises the oxidizer, the liquid oxygen, to the same pressure as the CH4 boost pump does. That enables a little bit of the fuel and all of the oxygen to be at the same pressure. And this also goes up to the far right of the image, the pre-burner injection manifold. That kind of goes out that way. So then we actually see what's next is the turbine manifold. And the turbine manifold is not actually connected to the Lox Turbo Pump except through a sealed shaft. That is a sealed axle that runs the entire length of this assembly. There's no gas passage that way. What the turbine manifold is it takes the high-pressure methane and the high-pressure oxygen from those two pumps, And in the pre-burner injection manifold, it mixes them and burns them. And that creates very, very high pressure gas. Like I said, it might even be 10,000 psi. And this gas flows over a turbine, and the turbine spins. And this is what provides the torque, the power to that shaft that spins the CH4 turbo pump, the CH4 boost pump, and the Lox Turbo Pump. So all that's mounted on a single shaft. And then those hot, high-pressure gases actually make this right-angle turn to flow to the bottom of this picture, that hot oxygen-rich gas, and then it makes another right-angle turn to flow into the top of the combustion chamber. So after all that, we now understand what's going on in the power pack on this engine. So we're going to kind of step back and take another view at the engine, and this is sort of from the same aspect as the image that ULA has shared, but instead it doesn't have all that instrumentation and the wiring looms on it. And so we can get a great view of what I believe to be the fuel valve. So if you remember earlier, I said I didn't believe that the fuel valve was in the same place as the oxygen valve. And so I think this is the fuel valve, and it looks to me like it has a rotary actuator here that actually also acts as a trim valve. So that is that that valve controls the amount of fuel going into the preburner, and this is actually how you throttle the engine. By adjusting the amount of fuel you put into the preburner, you adjust the temperature and the mass flow through your turbine. This controls the amount of power going into the pumps. By reducing the amount of power going into the pumps, you reduce the amount of fuel and oxidizer that you're raising the pressure of, and so you reduce those flow rates, and you reduce that pressure very slightly. And by reducing the pressure, you reduce the thrust of the engine. So you can kind of see this is the back side of the power pack from what we were seeing earlier. So you can see that tube that brings the fuel from the boost pump up to the pre-burner manifold, and that's what that fuel valve's on. I also suspect that this acts as the main fuel valve. You can also see where that oxidizer tube delivers the propellant to the oxidizer turbo pump. You can see all of these curved tubes, and you can imagine how as things heat up and cool down, they bend and contract and adjust their shape without running into each other based on those images we were showing earlier. So this is, I think, a really excellent image kind of showing a lot of the concepts that we've discussed here earlier. So I think we've talked about most of the big tubes that exist on this engine. That is to say that we've looked at all the major pieces of hardware that we can expect to see here. So now I want to talk about some of the smallest pieces of hardware we'll see, because there's a lot of them. Here we see 5 different things we can look for all around the engine. The first thing on the upper left is called a check valve. A check valve allows gas or fluid to flow through it only in a single direction, and usually it does this by having a ball in it that's spring-loaded in one direction, so that when fluid flows against the spring, the ball kind of moves backwards, allowing fluid to go through. But when fluid tries to go the opposite direction, the spring slams the valve shut, and then the fluid pushes on the back side of the ball, and that creates a seal that prevents fluid from going the other direction. And these are used all over the place to prevent gases and fluids from mixing, to prevent combustion gases from getting somewhere where they shouldn't, to prevent little drops of fuel from flowing back up a gas pressurization line and maybe getting somewhere where they shouldn't. So check valves are found basically all over the place in a rocket engine. So you can kind of tell them they're these like cylindrical fittings with these nut-shaped widgets on either end that have tubes sticking out of them. They'll be slightly larger in diameter than the rest of the tube they're associated with. The other thing we can look for are pressure transducers. Pressure transducers have a little piezoelectric element that changes its voltage based upon the pressure that's pushing against it. And these pressure transducers are found all over the engine because measuring pressures is one of the primary things you need to accomplish when you're controlling a rocket engine. And pressure transducers come in a couple of varieties. They come in absolute reference pressure transducers, where you pull a very tiny pocket of vacuum in the back of them on the other side of that piezoelectric element, so you're measuring from the pressure from kind of absolute zero. They come in kind of standard reference versions where they measure the pressure in relation to ambient pressure. And then they come in DP versions, that is delta pressure versions, where actually you plumb a tube into either side of them and you measure the difference in pressure between the two of them. And these can be incredibly, insanely accurate, and you can actually use these to tell how much fuel you have in your tanks based on the head pressure, that is how much the fluid pressure is across the tank. So these DP sensors are absolutely essential for measuring the amount of propellant you find in them. And so you can find pressure transducers all over the engine. Some other things we can look for are solenoid valves. Solenoid valves come in both 2-way and 3-way configurations. kind of the lower two you can see are Murata configuration solenoid valves, so those would be very common on any rocket product, and the upper one comes from a different vendor and is a slightly heavier, more ground support-esque version. So these solenoid valves allow you to turn an electrical control signal into the flow of a gas, and typically then this gas is used to control a pneumatic piston or a cylinder or a rotary vane or something that can open or close a much larger valve. So these are typically pilot solenoids, not direct-acting solenoids. And you can find solenoids all over the engine. Kind of at the bottom middle there, you have an engine controller. These are sometimes called FADECs, Full Authority Digital Engine Controllers. These amalgamate all of the signals from the avionics, and they provide all the control signals to the solenoid valves, and they check all the pressures and speeds and the thermocouples, they measure temperature, and they allow computer software to read and store and act on all of that information. And finally, one of the most ubiquitous pieces of hardware you'll find around a rocket engine, aside from generic nuts and bolts, is called a P-clamp. And P-clamps are used for all kinds of things. So P-clamps are used to rigidly mount many of these other components to the rocket engine. So for example, you can imagine a P-clamp that grabs onto a pressure transducer or a check valve, or sometimes even just a tube or a bundle of wires can go through a P-clamp. So these comes in all shapes and sizes. Typically, they're a metal clamp with a silicon cover to prevent the metal from chafing on the wires or the tube and causing damage in the extremely high vibration loading environment of the rocket engine. So we can actually look back at that original image shared by United Launch Alliance and take a peek for some of these things we know to look for now. So you can see circled here in purple, there are several engine control units, and I suspect that probably not all of these are control units. Some of them might be analog to digital converters, reading signals in from the pressure transducers and the thermocouples and the turbine speed sensors and converting them into communication signals that it can send back to a single larger engine control unit. And to be honest, I poked around for several minutes tracing wire harnesses and wire looms, trying to find where that full authority digital engine controller was, and I didn't have a lot of success. I suspect it might be the one kind of in the lower right, but I know for sure there's at least one that I can't see, so it's possible that it may also be hiding from me. So here's another image where we can show off some of the little features we know to look for now. You can see a lot of pneumatics tubes that have actually been capped off at the end. So those would connect to something that we can't see. Those are kind of in the upper middle of the image. Kind of hiding right up against the top of the power pack, we can see a pressure transducer held in by two P-clamps. We have a bracket panel that has a variety of fittings on it. I suspect that this is a hookup to the pneumatics lines on the rest of the rocket. And actually, you can kind of see that that transducer leads to that hookup panel, so the transducer might be reading the pressure on one or all of those pneumatic lines. Kind of near the bottom middle of the image, we can see that Lox inlet again. And this Lox inlet has a pneumatic line that actually comes off at 90 degrees to the flow angle. And I suspect that this is actually going to one of those DP pressure transducers. You can create a fairly accurate mass flow sensor by measuring the pressure of the propellant at one location and the pressure at another location. And by knowing something about the cross-sectional area relationship of these two locations, you can do some math and calculate the change in dynamic pressure and use that to calculate what your mass flow is. I suspect that this is probably a development engine and that maybe not all of the things we've seen in the images before this will be present on the flight version of the engine, but we can't know for sure. I have no particular knowledge of the inside workings of Blue Origin, but I do look forward to seeing this engine fly whenever it flies, whether that's on New Glenn or Vulcan, hopefully in the near future, and hopefully in a reusable configuration, helping to make humanity a multi-planetary species. While we're waiting on that flight, I will keep working on my own liquid rocket engine on my liquid rocket engine series and my solid rocket motor on my solid rocket motor series. If you'd like to support either of these projects or random spontaneous videos like this one, you can support me on Patreon. And until my next video, I wish you good luck and Godspeed.